So we have a Newton's second law problem in rotation. We have two disks. So here we have two disks that are concentric and welded together. So they rotate together. They also rotate around this axle. And one disk has a 0.12 meters radius. The other one has 0.24, so twice as big. So let me just mark here. This is 0.12. This is 0.24. Okay. And they were both cut out of thick metal sheets with 254 kilograms per square meter density. So the mass was not directly given, but we were given the dimensions, so we can find the area, and we are now given the area density. So with area and area density, we can find out the masses, right? Then you wrap a long and massless string around the smaller disk and hang a 0.15 kilogram mass at the other end of the string. The mass is held at 1.4 meters above the floor. You release the mass from rest. Both disks rotate together. Of course, they're welded together. And how long does it take? So how long does the time ask? This seems to be kinematics. How long does it take the mass to fall to the ground, and at what speed? And at what speed could either kinematics be kinematics, or it could be energy conservation if there's no friction. It seems like there's no friction. But since we need this time here, we'll likely have to get kinematics, which means we need acceleration, and that comes out of a Newton's second law in rotation we're going to use today. And the speed is either way, but since we're going down this route, we get speed through this method. So first of all, let's find out the mass of the disks. So let's do some generic calculation. That mass is equal to area density, surface density, sigma times area, and that's equal to, in this case, surface density times pi and r squared. And we have two different radii. So the little r, let's say little r equals 0.12. That's for the smaller disk. So this m of the smaller disk is just sigma times the area, the pi little r squared. And the rotational inertia of a disk, we know that is rotational inertia of a disk is 1/2 mass of the disk times radius squared. This is a solid disk, so 1/2. The mass gets replaced by the sigma pi and r squared, and then we have this additional r squared, so r to the 4th power. Okay, so the other disk, the mass of the 2r radius disk is the same, so sigma times area pi and 2r's square. So the rotational inertia of that 2r radius disk is 1/2 the 2r radius mass and the radius of 2r squared. It is equal to 1/2 sigma pi. Then you take this 2r, you square it, you get 4r squared. You take this 2r, you square it, you get another 4r squared. And instead of combining these with the 1/2, I want to keep the 1/2 out so that we can see how the total rotational inertia can be calculated. So 1/2 sigma pi r to the 4th power, everything times 16. So that is the 2r. And then what about the I total? We need that total rotational inertia. That should be the IR plus I of 2r, so the small and big disk. And you realize this is the same as that part, except for that 16 times. So now we can say 17 times 1/2, right? So it's 17 over 2 sigma pi r to the 4th power. So this will be related to the rotational angular acceleration and the torque on the disk. Okay, so now we're ready to start our calculation. We can look at this diagram and see where torques are applied. So we need to, well, define our axis rotation. It's typical just to choose right here. Let me use a different color pen, make it easier. So this is going to be our axis rotation. Let's pick this as axis of rotation. So we'll just say axis of rotation, just as that color. So maybe we'll put an O there, so that's equal to O. And then lever arm of the tension force. Tension applies from here and pulls downward, right? So this is tension. And this is the perpendicular distance between tension and the axis rotation. This is the line of action of tension. It extends infinitely in both ways, right? So this is perpendicular. So this red line here, horizontal line, this is that lever arm of tension. So I think I'm running out of space, but let's see, L, T, there. Okay, so that's the only torque. The gravity on either disk acts at the center through this axis rotation through the center, so they don't have any lever arms. So we'll summarize here. So let's change color back to black. So we pick the axis rotation, and we realize that let's see, L of tension is equal to this little r, 0.12, and L of gravity, actually in both cases, both disks, let's just call the total disk, is equal to 0. So is L of the support from the axle. And we usually don't mention that because we already know we put our axis rotation right there. So now we have this. If the say if the disk is were not uniform in density, then gravity does not act through that center, then this lever arm will be non-zero. But still the support, the axle, will have a 0 torque because that's exactly where the axis rotation is. All right, so let's do this. We'll divide this area, this whole writing space in half because I don't really need that much space. So we'll do 2 columns from now. And the next thing we want to do is to use Newton's second law in rotation, which reads tau is equal to I alpha. This is the net torque. We only have one torque anyway. And the torque from tension is equal to, and this is if you think about which way the tension tends to rotate the system, tension tends to rotate the system this way, right? This is actually clockwise. We should have a negative torque. So let's follow that. So a negative torque, tension times lever arm tension. So this is, let's use just a capital T for tension because we were using that. So this is equal to minus tension times R. We'll use R here because we can later maybe divide them out, right? So this is equal to I alpha. And since we're rotating this way clockwise, the alpha is actually going to be, this is alpha's direction, is into the board, because if you take a right hand and try to wrap your fingers around that clockwise direction, your thumb points into the page or the screen. So is this torque from tension is also into the screen. Okay, so now we know this acceleration is a negative quantity. So acceleration is negative quantity because it's clockwise acceleration, angular acceleration. Okay, so now we can use this equation to solve tension. Not really solving, just express tension in terms of the other quantities. So tension equals I alpha over R. And we also have this relationship that alpha is equal to A over R, but this is only magnitude, right? Acceleration of the linear acceleration of the block. I like to set up the block to have a downward pointing coordinate so that the acceleration will be positive. But maybe I can also set it up as upward pointing. So in this case, it really depends on which way I set my axis for the box, the falling box. So if let me move to the right side. If I set up my axis to point upward, say this is my axis, and this means the acceleration, I know the acceleration of the box is downward, so the acceleration must be a negative quantity. And since the angular acceleration is also negative quantity, clockwise, so there will be no negative sign here. So it's just a plus. They're both negative. So by the way, this is also negative, judging from how the box is going to fall down and which way I set up the y-axis. All right. So with that said, I can replace the alpha. So tension now is equal to, the negative is missing here, put that negative in there. So is negative I A over R. So there's already an R in the denominator, so this will be the square of that. So this is tension. This makes sense. Tension needs to be a positive quantity. I mean, just the magnitude of tension, right? So the A is negative and there's a negative, so this tension is a positive quantity. I just want to do that. Tension has a positive magnitude. Okay, so that is Newton's second law of rotation. Now we're back to Newton's second law of translation on the box, right? So on the box we have mass acceleration equals F. So that. And the net force, because we set up our axis to point upward, all the upward forces will be positive like this. All the negative forces are the downward ones. This is equal to mass acceleration. We know tension is less than gravity, otherwise the box wouldn't accelerate down, right? So this left side is a negative quantity, and the right side, as we already assumed, A is negative, so the right side is also negative. Since now we know tension already, we can plug it in. So we get negative IA over R squared minus this M is mass of the box. Should be clear enough. We had different masses for the different disks here and here, and this one has no subscript, is that Maverick box. Okay. So now we have the unknown A here. We'll combine the terms. Minus mg equals I over R squared plus m A. So A is equal to negative quantity mg, this is a ruler, over I over R squared plus m. So let's plug in the values. This m is the falling mass, 0.15, so 0.15 times 9.8 . Okay, so this quantity I here, I think I forgot to calculate this. Let's go back to this line here. We should calculate this quantity. 8.5, that's 17 over 2 times 254 times 9.8 times 0.12 to the fourth power. So this is equal to 1.406 kilograms meter squared. Okay, we just have enough space for that. So 1.406 over 0.12 squared plus this mass is 0.15, right? So the acceleration is a negative and a small quantity. We have minus 0.015 meters per second squared. Okay, so at this moment we have done our dynamics, we have gotten acceleration, and we'll be doing the one-dimensional translational or rotational kinematics. I like to do the translational because I know that 1.4 meter of descent. So let's do this. Now we have our choice to do our kinematics in 1D, and in 1D we're used to the x-axis, so let's point x-axis downward conveniently. So we'll start from 0 height. Okay, start from 0. I didn't go through the center, but that's okay. So start from 0, the x will reach 1.4 as the box reaches the bottom, reaches the ground. So we'll have this situation: x0 equals 0, x equals 1.4, v0 also starting from rest 0, and v is equal to, we don't know, we wish to find out. And acceleration is this very small quantity. Now that x points negative of y, a negative quantity in y will actually be a positive quantity in x. So there you go. We don't really know how long it takes. So these are the two questions we're asked: how long does it take and how fast? So the equations, let me remind the audience, these are the equations. Alright, so these are the equations. Let's plug in some numbers and just write the this on the right side. 1.4 equals 0 plus 0t plus 0.5 times 0.015 t squared. So now we have, that's a 0, so 1.4 equals this thing, t squared. So we can solve for t. So let's solve t here. T is equal to 1.4 over 0.5 times 0.015 square root, and that turns out to be 13.6 seconds. Okay, so now we have this. This is it sounds similar to a rotational inertia lab that we usually do in introductory physics lab. So 150 grams weight pulling a rotational stage with a sizable mass on top, a disc shape. Okay, so that is reasonable to me. And now we have time. The time can be plugged into this v, initial 0 plus 0.015 times 13.6. So how fast the speed? (0.205 meters per second). Okay, so if you, in case you wonder, you can check this speed out with energy conservation. Energy conservation, this is alternative for finding the speed. You can use mechanical energy, which is equal to the rotational kinetic energy of the disks, the translational kinetic energy of the mass m, and the gravitational potential energy of that mass m again. So this expression is 1/2 I, this I think I used total omega squared plus 1/2 mv squared plus mg. There's a height. Let's put a height there. We also have the relation that omega is equal to v over radius. This is the radius the strings wrapped around, not on the large disk, but on the small disk with the radius only r, right? So you can replace that and get this into an expression of energy. So then you can have E1 equals E2, right? E1 is everything is released from rest. The mass is at 1.4 meters above ground, and E2 is the mass is reaching 0 height, and things are moving. So this side is just mg 1.4. This side is that 1/2 I total v squared over r squared plus 1/2 m v squared and plus a0 mg0 height, right? So height equals 0. So you can, well, you can easily solve the V. It's a lot easier, but you do not get the kinematics parameters such as acceleration or time. So using energy conservation has advantage if you only have to know the velocity, but it has this distinct disadvantage that you have to go and find time another way, which means you have to find and analyze the forces and torques again, which is inconvenient. Thank you.